Okay, let's dive right into this. Welcome back to the Explainer. Today, we're zooming in on section 7.2, a fundamental concept in machine learning that basically bridges the gap between simple, isolated tests and real-world complexity, multi-class classification. You know, you've probably heard a million times about how algorithms catch spam emails, right? It's the classic go-to example of sorting data into exactly two buckets, spam or not spam. A super straightforward yes or no. But think about the real world for a second. The data we're dealing with out there is rarely that clean. If an algorithm is trying to identify what's in a photo or gauge the actual mood of a customer review, how does it choose between 3, 10, or literally 100 different categories? Moving past that basic binary logic is exactly what we're unpacking today. Let's just anchor our understanding real quick with a direct comparison. Binary classification is your classic spam versus not spam or sick versus healthy, exactly two classes, no middle ground. But the second we expand out from that, we cross over into multiclass classification. You might also hear it called multinomial classification. This is our territory anytime a problem involves 3 or more distinct classes. Now, what's really interesting about this slide is how elegantly simple the math looks when we actually define the problem. In multi-class classification, the target label, which we just call y, can be any one of C classes. So mathematically speaking, y belongs to the set of numbers from 1 through C. It looks so neat on paper, but underneath that simple little notation lies a massive practical headache for data scientists. How do our learning algorithms actually juggle all these multiple options at the exact same time?
That brings us to our first group, the naturals. These are the algorithms that just adapt easily.
We have 3 prime examples of these naturals. First up, ID3 decision trees. They adapt really easily just by calculating probabilities for all C classes at once. Next, you have logistic regression. It naturally extends itself by taking its standard binary curve, the sigmoid function, and basically upgrading it to a softmax function that elegantly balances the probabilities across multiple classes. And finally, k-nearest neighbors. It uses beautifully straightforward logic. It finds the k closest examples to a new input and literally just returns whichever class shows up the most. So, the crucial point is, what happens when your algorithm isn't one of these naturals? What if you're looking at a multi-class problem, but the specific tool you want to use is strictly binary by its very nature? A perfect example of this is the support vector machine, or SVM. As incredibly powerful as SVM is, it just cannot naturally be extended to multi-class problems. So what do? Do we just throw the whole algorithm out? Definitely not. We use a workaround, specifically the one versus rest strategy. To bypass the algorithm's limitations, we use this brilliantly clever hack. Let's walk through it step by step using a hypothetical 3-class problem. Say our possible labels are 1, 2, and 3. Step 1, we literally just create copies of our original dataset. Then we start messing with them. In the first copy, we take all the labels that are not 1 and we overwrite them with a 0. So boom, now we're just comparing class 1 versus a generic 0. In the second copy, we replace everything that isn't a 2 with a 0. And in the third copy, anything that's not a 3 becomes a 0. And just like that, look at what we've pulled off. We have entirely bypassed this structural limitation of the algorithm. We've transformed one messy problem into 3 separate, distinct binary problems. Our model just has to learn to distinguish 1 from 0, 2 from 0, and 3 from 0. We've built 3 separate classifiers all ready to go to work. But here is a puzzle for you. When a new input feature vector actually comes in, we have to apply all 3 of these newly minted models to it, which means we get 3 different predictions back. How exactly does the system pick the actual winner? If multiple models are triggering at once, how on earth do we synthesize these 3 binary outputs into one definitive multi-class answer? Well, the rule is actually quite simple. You pick the prediction of a non-zero class, which is the absolute most certain. It's not just about what the models are guessing, it's about how confidently they are making that guess. This ultimate tiebreaker relies heavily on a certainty score that gets generated by each individual binary model. Take a look at this quote directly from the source material. The larger the distance, the more certain is the prediction. Now, wait, why are we talking about distance? Well, in our support vector machine example, this certainty score isn't some probability percentage. It's an actual mathematically calculated physical distance, specifically the distance from the input point to the decision boundary. The further away that input is from the dividing line, the more confident the SVM model is about its prediction.
And this brilliantly illustrates the difference in how these algorithms measure their own confidence. If we were using logistic regression, our certainty is a probability, a clean score between 0 and 1. But with SVM, that certainty is literally the geometric distance to the boundary. But here's the thing, regardless of how they calculate it, both methods give us a hard quantitative metric. And that allows our one versus rest strategy to confidently pick the single most certain class and declare it the final winner.
So there we go. We've successfully hacked our way into making multi-class predictions. But we all know models aren't perfect, right? If an algorithm trained on animals mistakenly predicts cat instead of panther or mouse instead of rat, how do we actually spot those specific patterns of failure when we're dealing with dozens of classes? The answer lies in a really powerful tool called the confusion matrix, which maps out those exact cross-class mistakes. But that is a deep dive for another time. I hope this explainer gave you a solid conceptual grasp on how machine learning algorithms leap from simple binary choices into complex multi-class decision-making. Think about how these concepts apply to the AI you interact with every day, and I will see you in the next explainer.